Hi everyone. In this video I wanted to touch on how we actually roll electromagnetism into these ideas of quantum mechanics. And actually it's a very simple formula. It's right here. So basically we adjust the de Broglie wavelength with this little piece here, which is the vector magnetic potential. This is probably why people don't normally talk about this, is because people don't talk about the vector potential when they discuss electromagnetism. But we did touch on it when we talked about how the fact that Faraday's law introduces curl into the electric field, that requires us to revise the way the electric potential works, and we have to introduce this magnetic potential. Well, here it is again. It actually affects the wavelength that's associated with these quantum mechanical particles. Now, for a long time, the magnetic potential was actually well known to Maxwell and those guys who were investigating these things. But to them, it was just a mathematical convenience. I mean, really, what's fundamental are forces, the electric force, the magnetic force, and things like that. And strictly speaking, you don't really need the magnetic potential to understand those things. It's kind of a nice thing to know about, but it doesn't solve any extra problems that wouldn't be solved with just the fields. Now, this experiment here, this Aronoff-Bohm effect, is actually showing that there is a situation in which the magnetic vector potential is more fundamental than the magnetic field itself. So the idea is that you set up a double slit experiment, just like normal. You have electrons, they flow through two slits, they combine together. You get a classical, or the normal, double slit interference pattern. No problem. That's, now with our new understanding of quantum mechanics, that's what we expect to happen. What Aronoff and Bohm suggested was take a solenoid. Okay, a solenoid here, it's just a spiral of wire, an electromagnet. Inside that electromagnet is a magnetic field, and if this were infinitely long, the magnetic field is completely trapped inside. Remember, the magnetic field wants to curl around current, but if it's constrained in this spiral, it can't curl out because there's always more current. And so basically you've got a long straight line of the magnetic field, which acts as a bar magnet. So put that right behind the double slit. Now there's no magnetic field outside the solenoid, so you would expect no impact to the diffraction pattern. But there is an impact of the diffraction pattern. It gets shifted slightly. And the reason that's happening is because, I don't have it in the picture here, but the vector potential is not trapped inside. It actually extends out. And so the clever thing about this construction is that you have a situation in which you've got no magnetic field out here, but you do have a vector potential. And that vector potential follows the current. It doesn't curl around like the magnetic field, it follows the current. So if I've got a spiral of current, I'm going to have a spiral of that A field. Okay? So what that means is that if the A field is going in a circle this way, over here it's going to contribute to this momentum, in effect decreasing the wavelength over here and increase the wavelength over here. I get different wavelengths whether I'm on one side or the other. That difference in wavelength is going to affect the interference pattern I get. And what ends up happening is that they combine together here, but there's going to be a shift. That shift is a measurable effect of this difference in the de Broglie wavelength. So now that we have a de Broglie wavelength that's tied directly to the vector potential, we have a way of measuring it. And this is a clever example of really emphasizing the fact that this vector potential, which looks like just a mathematical add-on, is really the fundamental force or the fundamental quantity. The magnetic force is the derived quantity, and that's what I wanted to say.